Hello, everyone. My name is Linda Zhu, and I'll be talking about the phenomenology of a CP-violating Higgs portal dark matter model. This is work that I've been doing with Katie Fraser and Aditya Parikh at Harvard, fellow grad students. And if the stars align, this paper should be out about the time that the conference is going on, so go look for it. So, for a primarily cosmology audience, I won't motivate the importance of dark matter, but I will remind everyone why we liked the WIMP paradigm so much. It has very compelling theoretical motivation and a very compelling cosmological history. That is, the idea that the present day abundance is set by the freeze out of annihilation is very compelling. And there have been numerous experimental anomalies, the most famous Galactic Center excess that I'll talk about in the next slide, and also the less established and more recent AMS antiproton excess, both can point to a dark matter annihilating at and with the mass range of a WIMP scale dark matter. And the main thing that has tamped our enthusiasm in the recent years is these universally null results from a plethora of ground-based direct detection experiments that have set very stringent bounds on the dark matter nucleon scattering. So, framed in this way, what we're actually saying is that the attractive parts of the WIMP paradigm are primarily in its annihilation, and the detractive points are in its scattering with standard model particles. Or a successful WIMP model in the modern day, all it needs to do is to realize a large amount of scattering while a large amount of annihilation with a very small amount of scattering. And this hierarchy needs to be about 10 orders of magnitude. So a little bit more about the Galactic Center excess. This is a pretty large excess of gamma rays, and whose existence is pretty robust, but whose origin is pretty controversial. So the main debate lies between these unresolved point sources or a smooth emission of annihilating dark matter. If this excess is caused by the latter, the data prefers a 60 GeV dark matter with a WIMP-like cross-section annihilating with primarily Higgs-like branching ratios, so dominantly to BB and tau tau. So that was the introduction, but the main plan of the talk is simply to present this dark matter model and present some UV completions and discuss the constraints that both of these would face. So first things first, the dark matter EFT. The point is simply to develop a model that has all the attractive parts of a WIMP and is a good candidate for the Galactic Center axis while respecting the current scattering bounds. So we have a Meron fermion dark matter that couples to the Higgs portal with a complex coupling, CP-violating. The relevant parts of the Lagrangian are here. The real part of this coupling governs a scalar interaction, the imaginary part governs a pseudoscalar interaction, and then we generically allow coupling to the Z as well. So why, right? What does this win us? Well, so in the annihilation picture, in the non-relativistic limit, the scalar term, annihilation, is p-wave suppressed. So the annihilation dominantly happens through the pseudoscalar coupling, or the imaginary part of this Higgs coupling. On the scattering side, in the other hand, in the non-relativistic limit, the pseudoscalar scattering is suppressed, and the spin-independent scattering dominantly happens through the real part of the Higgs coupling. And the spin-dependent scattering is set by the Z coupling. So the three ways to detect cosmologically abundant dark matter is annihilation and two types of scattering experiments. And these three avenues are governed by three independent degrees of freedom. So to set the aforementioned hierarchy between annihilation and scattering, we have two options. The first one is sort of the traditional method of achieving this hierarchy, which is for a small amount of coupling, you can enhance the annihilation by tuning the dark matter mass to like very close to 1/2 the Higgs mass. This is typically called the S-wave resonance. But this model allows for a different avenue, which is for a comparatively large coupling, we can suppress the amount of spin-independent scattering by tuning the phase to make the coupling close to imaginary. So this EFT is then fully described by the dark matter mass, the magnitude and the phase of the Higgs coupling, and the magnitude of the Z coupling. And the constraints that we'll have to contend with are on the direct detection side. We'll take the most stringent of the currently available constraints, which happens to be xenon 110, and we'll also show the projections for the next generation LZ experiment in dotted lines here. And on the annihilation side, the requirement is simply that the annihilation cross-section is between 1 and 10 picobarns. That is not too small and not too large. So the top two plots here are essentially the picture that I was talking about before. That is, on the left, for a relatively small coupling, what happens is the annihilation needs to be enhanced. So this requires the dark matter mass to sit very close to the Higgs, to 1/2 of the Higgs mass. There's pretty large freedom in the phase the coupling can take, but the requirement of annihilation enhancement constrains the mass to be pretty tuned. On the other hand, on the right plot, for a relatively large coupling, what needs to happen is that the scattering needs to be strongly suppressed. So the phase requirement here is very stringent. The phase needs to be pretty close to pure imaginary, and then there's a comparatively huge amount of freedom in the values that the dark matter mass can take. On the bottom, we see that the spin-dependent scattering essentially sets an independent constraint on how large the Z coupling can be. So that's pretty much the entirety of the statements for the dark matter EFT. There's a few problems, one of which is that I've introduced the theory that's not gauge invariant, so we're gonna have to fix that. And so I'll introduce some pretty minimal UV completions here. The goal is to, of course, get a theory that isn't gauge anomalous and has at least one free phase so that we can do the CP violation thing. And of course, we want consistency with all known constraints, the new ones that come with all the other things that we will introduce. So one of these possible realizations is singlet-doublet dark matter. The players here are an SU2 singlet and an SU2 doublet pair, which in total give us 3 Majorana degrees of freedom and 1 Dirac one. We introduce Yukawas, which together with the 2 mass terms give us 4 couplings, and that with the 3 possible field rotations, the singlet and the 2 doublets, give us 1 free phase in total. We'll make the choice that these 2 Yukawas have the same phase, and that phase parameterizes the amount of CP violation present in this UV completion. So at this point, the model is fully specified by the singlet mass, the doublet mass, the 2 Yukawas, and the amount of CP violation. Now, the introduction of these Yukawas mixes these neutral particles, and so what shakes out is the 3 Majorana mass eigenstates are mixtures of singlets and doublets, and the lightest of this is the dark matter. There's only 1 charged fermion, so there's no mixing that happens there. Okay, so that's the singlet doublet. An alternative to this is the doublet-triplet dark matter model, which is, in addition to the 2 doublets that we saw earlier, there is an SU2 triplet rather than a singlet, which shakes out to 3 fermions. That's 3 neutral fermions, but 2 charged ones. And the Yukawa picture is pretty much the same. We end up with 1 free phase, and we make the same choice as before. So the model parameterization is almost identical, except with the triplet mass instead of the singlet mass. But because this is a triplet this time, the Yukawas induce mixing in both the neutral and the charged sectors. So both the 3 Majorana and 2 Dirac charged fermions are mixes of both the doublet and triplet terms. So the problem with introducing a complete model is you introduce more moving pieces, and that gives you more constraints. So the three types of new constraints that we'll have to deal with are constraints from the fact that um, we've developed a gauge consistent theory with CP violation, the current constraints that come with the fact that we've introduced a bunch of new particles, and the constraints that we have inherited from the EFT. So in order, for CP violation, we will mostly contend with EDM measurements that place pretty stringent bounds on the amount of CP violation that is coupled into the standard model gauge theory at low energies. For the new particle content, because nothing that's heavier than the dark matter in the dark sector is cosmologically abundant, to search for it, we will need to look at collider production, and these statements typically just mean that these new particles can't be too strongly coupled in, and they can't be too light. And the constraints from the EFT is essentially the stuff that we talked about before. We need suitable dark matter masses, dark matter Higgs couplings, and dark matter Z couplings that shake out from the singlet-doublet parameterization and the doublet-triplet one. So these are statements that the lightest particle needs to be about 60 GeV, like can't be too far off, it can't be like 2 or 200. The Higgs dark matter coupling needs to be either small or imaginary, it can't be large and very real. And the Z coupling needs to be suitably small. So it turns out that it's pretty tricky to find viable parameter space for the doublet-triplet model. So for the purposes of this talk, for the purposes of time, I'll mostly be talking about the constraints for the singlet-doublet one. The doublet-triplet case can be found in our paper. So first off, for the CP violation, we will be primarily contending with the electron EDM measurements put out by the ACME collaboration pretty recently. The contributions from the singlet-doublet dark matter model are given by this single Bar-Z diagram, and the dependencies shake out to be proportional to the product of the Yukawas, the amount of CP violation, and the doublet, weighted by the doublet mass. On the plots on the right, where the ruled out parameter space is shaded in teal, we find that the requirements are essentially that the coupling is sufficiently small, the CP violation is sufficiently small, or the doublet mass is sufficiently large. Any of these can give you viable parameter space. For the collider bounds, we'll be primarily dealing with two things for this talk. The first of which is the Higgs to invisible decays that can be probed by colliders. This is proportional to, again, the amount of CP violation and the product of the Yukawas and the doublet mass, but only is a valid constraint when this decay is kinematically viable, that is, when the dark matter is less than half the Higgs mass. So while these constraints are pretty lenient in general, in that this measurement isn't very precise, for the choices of couplings I've chosen for these slicings, essentially what this amounts to is it cuts out all parameter space where the dark matter, the lightest eigenstate, ends up being lighter than half the Higgs mass. For the other part of collider constraints that we will talk about in this talk, what we need to contend with are the oblique SU2 corrections, typically parameterized by these S, T, and U, etc. parameters, where S and T are the most constraining ones. These are roughly proportional to the sums and differences of the squares of the Yukawas, respectively, and these dependencies can be seen here. Like the ones before, these parameters are weighted by the mass of the doublet. All of this essentially says is that the thing that parameterizes the amount of the dark sector coupling to the standard model gauge theory is the doublet. The singlet doesn't actually couple. Finally, inherited from the EFT are the annihilation, spin-independent, and spin-dependent constraints that we need to contend with in the language of the UV model parameters. So in these plots, the green and yellow lines signify the mass and phase lines of interest, essentially. The green line is where the dark matter mass is exactly half the Higgs mass, and the yellow line is where the dark matter Higgs coupling ends up being purely imaginary. So again, the colored regions are the regions that have been ruled out, and for annihilation, the allowed parameter space traces the mass resonance and becomes, and the requirement becomes more and more stringent as you go to higher and higher doublet masses, because higher doublet masses means you essentially have a more decoupled doublet, and the Higgs dark matter coupling becomes a lot smaller, and you need a larger resonance to get the correct amount of annihilation. For the same reason, the spin-independent constraint, which just needs something to be sufficiently small, becomes a lot more relaxed at higher doublet masses because of the small coupling. In addition to that, the spin-independent constraint allows a line tracing the line where the coupling is exactly imaginary. The spin-dependent case cares about neither the phase or mass lines and only cares about the doublet mass in this slicing. For sufficiently large doublet mass, the coupling is sufficiently small, and so the spin-dependent scattering rate is sufficiently low. So putting this all together, there are three new constraints from the UV coupled with three constraints in the EFD that need to be contended with. Putting that all together, the EDM essentially carves out all doublet masses below a TeV. The Higgs the Higgs to invisible constraint carves out parameter space where the dark matter mass is light. The SU2 and spin-dependent constraints essentially are subdominant to the EDM in this picture, and spin-independent drops off at the imaginary coupling, and finally the annihilation traces the mass contours. So what's left in white is the available parameter space for this particular slicing. Of course, it's kind of hard to explore the full five-dimensional parameter space in this talk, so you can see more slicings of this and better discussion in the paper. But if you zoom in to the available parameter space, you can see that in the white region over there, you can see that the allowed mass range is actually quite large compared to the typical mass resonance tuning pictures, where those masses need to be specified to typically like a 0.1 GeV. Here we have several GeV amount of freedom for dark matter mass for your viable parameter space, and associated with that we have a range of phase freedom as well. So I guess in conclusion, all we're trying to say is that this is a new viable model as a solution to the Galactic Center excess, and has all the good parts of a WIMP model without being ruled out, and without resorting to the aesthetically uglier S-wave resonance tuning. Several UV completions are possible. In this talk, I've mostly focused on the pretty minimal singlet-doublet dark matter model, and with that, there's pretty viable parameter space that can also be pretty accessible to the next generation of experiments. So, thank you.